Going back to where we left off last time, we were looking at this problem 754. It's a combination problem, that's why we're working it. What it is a pin fin attached to a base material. The dimensions are given: diameter, the height of the pin fin, the base dimensions. The base is being kept at a temperature 350 K, and the pin fin is exposed to convection heat transfer in air. The air velocity, 10 meters per second, the air temperature, 300. We're asked to find the total heat loss by the fin plus the base. Okay. We're going to evaluate the properties of air at 325, which is the film temperature, base temperature plus free steam temperature divided by 2. This goes back to chapter 3 of fins. And we worked last time, we worked through part of it. So here's what we did last time. Number 1, we said, first thing we want to do is find out, since this is now chapter 7, find out what H is for the fin. Okay, it's a circular geometry. Chapter 7, last part of chapter 7, circular geometry. So number 1, find convection from the fin. Step number 1, we have the Reynolds number based on the fin diameter. We know the velocity, we know the diameter, we can find the kinematic viscosity back of the book tables at 325 Kelvin. That's 1088. And then we use Hilbert equation, 752. To get H. Nusselt, based on diameter, HD over K. C, Reynolds, D to the M. Prandtl to the 1/3. C and M, table 7.2. And we get H bar equal 221. Use table 3.4, we said last time, to get Q fin. Remember table 3.4, fins of uniform cross-section. This is a fin of uniform cross-section. In table 3.4, there are 4 options: convection at the fin tip, adiabatic fin tip, prescribed temperature at the fin tip, and the model which says the fin behaves as if it were infinitely long. We said the easy way out is that case D. See if it can be modeled as an infinite fin, because QF is ridiculously simple. Okay, and we did that, and you couldn't do that. We checked the ML value. It was less than 2.65. So we couldn't use case D. We had to use case A. I'll put it down here, case A. And of course, that was the more complicated equation, capital M, parentheses, our hyperbolic sign, ML. And then we had the H over MK, hyperbolic cosine, ML, divided by hyperbolic cosine, ML. Hyperbolic sine, ML. 0.815 watts. And we mentioned, oops, let's put a bracket on here. We mentioned, I'll just mention again, K, they're not the same. Don't get confused and put the same K in both equations. It's not going to work. One is air, one is a fin material. I think it was copper. Okay, so that's where we left off last time. Now, to get we could use table 3.4. Table 3.5. Figure 319. We did. We just used table 3.4. The choice is going to be yours, though. You've got to figure out which of those three you're going to use to get Q. Some may work and some may not work. Let's go to the one that won't work. Figure 319. No. Just to refresh your memory. This is figure 319. A to F versus some parameter on the x-axis. This is for a, let's do it the other way. The book shows it the other way. I'll get it right. Rectangular, triangular fins. This is a pin fin. A pin fin is not a rectangular or triangular fin. Obviously not triangular. Okay, so forget that. Here it is. Here's the fin. Here it is attached to the blackboard. That's this picture right here. That's figure 319. Okay. It's very, very long. Very, very long and out of the board towards you. Out of the board towards you. No, it doesn't model it that. No, it doesn't model that. No, So no. All right, we're going to use table 3.5. Okay, so we'll try it that way. Table 3.5. There's a picture there in table 3.5. It's labeled pin fin. Thank you very much. I know I can use it. It says pin fin. Now, though, we're going to use fin efficiency. So we'll review that. Chapter 3. Hyperbolic tangent, MLC, divided by MLC. In the picture, in table 3.5, he shows a pin fin, and he tells you what LC is. He said, when you use this equation, make sure you use LC. L plus D over 4. He tells you that in the picture, 12.5 millimeters. So now we know L sub C. Now we put this in here, and we get the fin efficiency 947, 94.7% efficient fin. Now we put that in the equation to find Q fin. Q fin, eta fin, area of the fin, H bar over the fin, T base minus T infinity. Make sure you get the right fin area. Don't forget, anytime you use this efficiency in the picture for the pin fin, always use LC. What's LC? The corrected fin length. That's the length the fin would be if the end of the fin were adiabatic and the fin lost the same heat as the fin with the convection on the tip. You can go back and review that from chapter 3. Oh yeah, they agree, really good. 815, 822, 7 parts out of 800, less than a 1% difference, less than 1% difference. Whether you use table 3.4 or whether you use table 3.5, you get the same answer. Okay, that's good. That's good practice then. Don't use figure 319, no, wrong. You got a choice. You always look at the fin geometry. Is it a straight rectangular fin? Is it a triangular fin? Is it a pin fin? Is it a circular pin fin? Is it a square pin fin? Is it a circumferential fin? That's number one. Find the fin geometry. Then make the choice where you want to go to find Q fin. Some work and some don't work. Okay, so that is how we do that guy. Now the base. We didn't do the base yet. There's the base, okay. Next, consider the base. Okay, Reynolds number of the base. Now, air is flowing over a flat surface. We're going to consider it to be a flat plate. Chapter 7, first part, chapter 7, flow over a flat plate. Maybe there's a boundary layer buildup here at the front. Oh, this air's going this way. Here's the front, x equals 0. Here's x equal L. Maybe a boundary layer builds up, and the boundary layer might be laminar, might be mixed, might be all turbulent. And so the Reynolds number, VD over nu, VL, pardon me. Let's make that like we do in chapter 7, U infinity. We know all that stuff. Put it in there, 2176. You say, well, okay, chapter 7, is that less than 500,000, 5 times 10 to the 5th? Yeah, it is. Okay, if it's less than 5 times 10 to the 5th, it's a flow laminar? I doubt it. I don't think so. Because I think that fin's going to really mess things up there. Oh yeah, it might start off as a laminar boundary layer. When it hits this guy, it's going to go crazy. There's going to be a wake region behind it. So I don't think it's going to be laminar. I'm not even going to consider mixed flow. I'm going to say, no, it's all turbulent. And we did that before. It's nothing new. We did that before in chapter 7. So I'm just saying again, we're going to assume it's all turbulent, even though the Reynolds number indicates that it should be laminar, because that fin's attached to it. Okay, the equation we use, let's see here, equation 783. Okay, here it is, H bar, K over L, and now we have 0.037 times Reynolds to the 4/5, Prandtl to the 1/3. I know all those guys. Put that in there, and I get H bar 107. So now I get Q equal Q fin plus Q base. Okay, so I've got my Q fin 0.815, Q base H bar, area of the base, T base minus T infinity. Two millimeters. The square minus the fin cross-section area gives us the base area where it touches the air. The area is where the air touches the base. Put that in there. There's H bar. So Q turns out to be 0.883. Yeah, there's the base, there's not a lot of heat from the base. You can see 0.883 minus 0.822. So most of the heat, of course, that's the idea. Why do you put the fin on in the first place? You want to take more heat out, a lot more heat out than the base would by itself. So attach the fin, and that cranks up the heat loss from the base material. Yeah?
Would it be 0.004?
It would be. Thank you so much. Thank you. It's funny, the answer is the same though. Okay, so that's a good review of Chapter 7, Chapter 3. That's why I chose that problem to look at. Okay, so anything else before I erase the first part of this and go to the next one here? Okay. I'm going to save that guy, but I'm going to put this one here is going to be different. Okay. Let's just get rid of him too. All right, so now I'm going to look at another problem, combined heat transfer problem. I'm going to give you a handout because it's a different textbook, and so you can read along with me. It's coming. Hang on. Okay, there we go. Okay, everybody's good. All right, so let me put down, first of all, where this problem came from. Different textbook. Okay, it's a very popular textbook. Author's been around a long time. Well written. It's a good textbook. And this was this was a good example of that textbook. So let's read it, and then I'll go through the math and equations. The crankcase of an automobile is approximately 6/10 meters long, 2/10 meters wide, and 1/10 meter deep. See the schematic, okay. Assuming that the surface temperature of the crankcase is 350 K, estimate the rate of heat transfer from the crankcase to the atmospheric air at 276 K that flows over it due to the automobile's road speed of 30 meters per second, which is 67 miles an hour. Assume that the vibration of the engine and chassis induce the transition from laminar to turbulent flow so near the leading edge that for all practical purposes, the boundary layer is turbulent over the entire surface. Okay, major hint. He says to you, assume turbulent flow over the crankcase, the sides and the bottom. You know our rule. The rule is if you get a problem on convection heat transfer over a flat plate, always assume it starts out laminar, maybe it transits to turbulent, mixed flow, and only if you see the words, assume the flow is turbulent, then you assume it's turbulent. But the problem has to say, assume the flow is turbulent from the leading edge. So that's number one. We would normally assume that the flow would be laminar at the start and then transits to turbulent. He says, too much vibration down there. Airflow is kind of messed up under the car. It's not a smooth, uniform airflow, obviously. Well, okay, properties at T-film. So properties at T-film. And if you take the air temperature and the crankcase temperature, the average temperature is 313 K. 313 K, got it. Air properties. Got it. Get the Reynolds number. The length of it is 6/10. The top is attached to the engine, so it's not exposed to air. Okay, so the top, forget it. It's attached to the engine block. We don't look at that. But here's the airflow. The airflow goes over the bottom, the back side, the front side, the left side, the right side. 5 areas. The front, the back, left, right, bottom. We're basing the Reynolds number on this length here, which happens to be 6/10 meters. So the Reynolds number comes out, as you can see, at 1.03 10 to the 6th. Well, it's greater than 5 times 10 to the 5th, but I don't care. He told me, irregardless, assume the flow is turbulent. Okay, it's turbulent. Then you use the equation in chapter 7, 738. To get H bar. Nusselt bar. H bar. K over L over K. L is 6/10. 0.037. Reynolds to the 1/3, Reynolds to the 4/5, Reynolds to the 1/3. He uses 0.036 rather than 0.037. Sometimes in different textbooks you'll find minor things like that. Maybe a slightly different correlation constant. That's okay. In our book, it's 0.037. So I'm looking at our book equation, 738 is a 0.037. This gives H bar 94.2. Okay, he says the area is equal to area of the bottom plus 2 times the area of one side plus the area of the front and the area of the back. Okay, and if you put those numbers in, it's 6/10 long by 2/10 wide. Put all those numbers in and you get an area of 0.28 square meters. And then he says, if you want to find Q, then just chapter 1, Q equal H bar A total times T surface minus T infinity, 1952 watts. Okay, any question on that before you go on then? Okay, so car's going 67 miles an hour. You're on the freeway, you hit traffic, all 4 lanes are blocked. You're going to sit there for 20 minutes, maybe 30 minutes. The engine might be running. The crankcase is getting hotter and hotter. You're trying to dump heat out of it by what? There's no air moving past it. Everything's still and calm. Free convection, chapter 9. So I'm adding to this problem. This problem didn't consider that in the textbook, but I'm going to add other things to this problem. So now, if the car is stopped, free convection. From the bottom of the crankcase. Okay. Chapter 9. The decision you got to make. What does the surface look like? It's a horizontal flat plate. Okay, got it. Horizontal flat plate. Second question. Is the plate hot or cold? Okay, the plate's hot. Got it. Third question. Are you looking at the top or bottom of the hot plate? The bottom. Got it. That leads you to the correct equation. Okay, so we go to equation 932. Bottom of a hot plate. Nusselt bar. Chapter 9, no more Reynolds number. Now it's Rayleigh number. Okay, Rayleigh number. I know everything. L is 0.6. I know alpha. I know nu. Beta is 1 over T film. G 9.81. I got it all. Put it all in there, 8.42 10 to the 7th. Got it. Solve this guy for H bar. Then find Q. That surface area is 6/10 times 2/10. Yeah. Horizontal plate. What's L, the plate length? No, that's not the plate length. Surface area over perimeter. .075 meters. Wherever you see an L in the equations, that's what you put in there. Now, don't forget that Q is only from the bottom surface, okay? That's 62.8 watts. But the interesting thing is the H bar value, the H bar value. Look when the car is moving, H is 94. Look when the car is stopped, 7. It drops dramatically when it's stopped. You're not going to get the heat transfer because it's still air on the bottom of a hot plate. Two bad news, stopped car and on the bottom of a hot plate. Okay, any questions on that before we go on? Okay, now I thought, you know what? Maybe that crankcase is losing heat by radiation. I mean, this is a heat transfer class. We got conduction, convection, radiation. You better check that. You better check that because you better believe if you just put these answers out in a conference paper you're doing, somebody's going to ask you, oh, by the way, did you consider radiation from the bottom to the asphalt street? Oh, no, because I didn't think it's important. No, don't say that. That will not be the response you want to say. You say, yes, I did, and I'll show you what I found. That's what you want to say. Okay, so now consider radiation from the bottom surface. Again, he didn't do that in that example problem, but I'm adding things to it for you. Radiation. Consider radiation just from the bottom. We could do the size. We'll just do the bottom. We're going to assume crankcase. And the road are black. That's a decent approximation. Black asphalt street, I'm going to assume it's a black surface. And that means, of course, epsilon for both is 1. So if you want to go to chapter 13 and model this by 3 resistors, there's 1 resistor, 1 minus epsilon of the crankcase divided by epsilon crankcase, area of the crankcase. This is the temperature of the crankcase. Then there is a space resistance, 1 over the area of the crankcase times the view factor from the crankcase to the road. I'm going to call it the surface. Yeah, I don't know. I'll call it the road R. Okay, and then we have another resistance for the roadway. This is the temperature of the roadway. This is 1 minus epsilon roadway divided by epsilon roadway, area of the roadway. And this is our Q radiation. Okay, we know the surface resistance. If the surface is black, the resistance is 0. Got it. If the surface is black, the resistance is 0. Got it. What am I left with? I'm left with Q radiation, and let's get these right. Don't use temperatures in chapter 13. Use the emissive power of the black surface. This is C. This is the emissive power, black surface of the road. Sigma T road to the 4th power, absolute. Everything's absolute, chapter 13. Okay, so, okay, got it. High temperature crankcase, low temperature roadway, divided by 1 over AC FC to R. Put those numbers in, 62.7 watts. I'm using a view factor 1.0. If this is the bottom of the crankcase, and how far is a crankcase off the ground of the car? I don't know, this far? What's the view from the bottom there to the floor? Oh, I'll tell you what it is. It's really close to 1. The closer I get to the ground, there, it's 0.99999. Here, it might be 0.4, 0.5, 0.6, 0.7, 0.8, 0.9, 0.95, 0.97. I'm just going to assume it's 1. I could take more time and maybe do a better job, but 1's fine. 1's fine. So, yeah, 1. So when I'm done, 62.7 watts. They don't care if the car is moving or at rest. I don't care. Works both ways. Interesting, this guy here, convection, when the car is not moving, 62.8 from the bottom surface, and the radiation is 62.7, really close. You can't ignore that guy when the car is stopped. You can't ignore him. They're almost the same. Oh, when it's moving, oh yeah, sure. 1,950. Yeah, that's different. Now, go back over here. Do I really believe that that H from that equation is valid on the bottom? Yes. On the front side? Yes. On the back side? Yes. Okay, here it comes. On the front? Oh, no. Give me a break. No. That equation we did is for about, here's a crankcase. Here's the engine above it. Let's say the bottom's open. Air comes here, hits this edge, boundary layer builds up. Great. On the bottom. Air hits here, boundary layer builds up on the bottom. Got it. The front. Air hits here, boundary layer. Oh, no, it's messy. Really messy. The air spreads out in all directions. And even worse than that, the backside, a wake region, turbulent eddies, a boundary layer back there? Oh no, not even close. So, I believe that. I don't believe those two guys. But this is just a first cut at the problem. This is a first basic cut. He said, I don't care, let's just assume the H is the same on every surface. Yeah, but you better be careful, because it's not even close on the front and the back. So you better find out how you do that. Well, you go to chapter 7, and I guarantee you it's in there. It's in the table there for that. And the table, I think I've got, do I have it here? No, let's see. Let's see if I've got that. Oh, yeah, table 7.3. It's for a flat plate. The picture in the book is a flat plate, just like this, and the air hitting right there, normal to the surface. So I would get another H. I would get two other H's. I'd have, here's the H for the bottom and the two sides. Then I'd find an H for the front and an H for the back. And that's much better to do it that way than assume the H is the same on all 5 surfaces. But a very, very good review problem. That's why it shows that one out of the Creeth textbook, because you can take that problem and expand it with other things. So this is a chapter 7, chapter 9, and chapter 13 combo problem. Okay, so yeah, that's how we bring all these pieces of heat transfer together after we cover 13 chapters in the book. We bring them all together to solve a more complicated problem. Okay, good stopping point for today.